Hello, my name is Peter Todd and my lab partner is Andrew Mickey. This is our video report for Lab 9 Diffraction in OPTI380 at the University of Arizona's Wyant College of Optical Sciences. In this lab, we explored how light interacts with apertures and how diffraction patterns change as we move from the Fresnel to the Fraunhofer region for various slit geometries, and finally measured the divergence of a Gaussian laser beam.
In part A of the lab, we observed the diffraction patterns caused by several different aperture shapes in both the Fresnel and Fraunhofer region by moving our camera closer and further from the apertures. These images show the progression of a single slit aperture as we observe from the Fresnel region to the Fraunhofer region. In the Fresnel region, very close to the aperture, we can see the very tall vertical slit aperture. As we move further along the optical rail, we observe that slit flattening and widening until in the Fraunhofer region we see our 2D diffraction pattern in the horizontal direction rather than the vertical direction. Next, we observed other shapes of apertures, including a triangle, square, and rectangle. The diffraction pattern stretched opposite to the flat edges of the shapes. For the double slit apertures, as we moved the two slits closer together, the pattern got denser and the spots got smaller. On the right, you can see a video of the transition of the double slit apertures from the Fresnel region to the Fraunhofer region. The final slit shape we looked at was a circular aperture. In the Fresnel region, we can clearly see the circular aperture. As we move into the Fraunhofer region, we can see the diffraction pattern, which resembles the airy disk pattern. However, there was likely some fingerprints and other impurities on our lenses and our diffraction grating that caused the imperfections that you see in our airy disk. We took this image into MATLAB and we analyzed it to fit a sinc function and a sombrero function. This shows the fit of our sombrero function. As you can see, we had many more spikes than matched the fit of the sombrero function. This is likely due to the imperfections I previously mentioned about our system. However, the primary slit is captured in both our sombrero function and our sinc function. Therefore, our MATLAB fit confirmed a close agreement between the experiment and the sinc and sombrero models.
In part B, we measured the divergence of a Gaussian laser beam by recording the beam width at various distances using a beam profiler. Using our data, we found that the beamed radius increased gradually from about 0.75 millimeters near 30 millimeters distance to just over 1 millimeter at 570 millimeters distance. We put this data into Excel and fit a quadratic regression to it. We used the found coefficients of that regression to find beam waste, as you can see below. Overall, this lab went smoothly and gave us clear results. We successfully observed the diffraction patterns for all aperture geometries in Part A, showing the transitions from the Fresnel to the Fraunhofer regions. From our beam divergence measurements in Part B, we found a beam waste of 0.28 millimeters compared to the actual 0.274 millimeters, a roughly 2% error. Our measured divergence angle in numerical aperture, still in Part B, closely matched theoretical predictions, confirming the accuracy of our Gaussian model. Finishing up after the time limit, but it's just the outro, so it's okay. This lab gave us hands-on experience exploring diffraction and Gaussian beam behavior, and it was fun. Thank you for watching.